Okay, then I guess I am almost ready here. Now I'm totally ready. So in this semester, we started talking about kinematics, and then we moved to the dynamics, or also known as Newton's laws of motion. And then we've been learning how to use Newton's laws of motion to solve problems, okay, in different kind of motion. For example, when object is moving horizontal direction or at inclined plane or circle, horizontal circle or vertical circle, right? So we've been learning about those. And then today we're gonna just continue learning about that. But we will talk a little bit more about the force we already used, okay? So we have already used this force of gravity. And we also said, okay, this force of gravity is the pull from the earth on us, okay? And we said, okay, that pull on us is weight of the object or our weight, okay? So that's what we said. So from that, it may sound like, okay, there is only this force of gravity coming from the earth. But if we look at details, especially the same person who provided us laws of motion also provided the law of gravity. So it's not just between us and the earth. According to Newton's laws of motion, it's the force between any two masses. If you have two masses, you have force of gravity, okay? So now in today's class, we're going to include that force of gravity for circular motion that causes the circular motion of heavenly objects like moon that goes around the earth or the earth that goes around the sun and so on, okay? So the according to Newton's law of gravitation, there are force of attraction between any two masses. So if there is one large mass and another one is small mass, in that case, what happens is small mass kind of goes around that larger mass. And why does it goes around in that nearly circular path? Because of the gravitational pull, okay? So now, just like we, for example, described motion of a ball tied to a string that goes around, over our head, just like shown in this drawing here, that is from our, ooh, I got this pointer, but once this pointer is selected, I cannot write it. That's not good. I thought I cracked the code. Turns out it's not. Okay, so it goes to the laser pointer, not on the pen. That's not good. Oh, looks like I forgot to share this screen, huh? Sorry about that. Oh, I had shared my screen, but these folks shared it and my screen went away. I did not realize it. Okay, sorry about that. So you are just looking at me, huh? Big head of mine. Okay, so this is the one I was talking about. See, I got this pointer to, hoping that it will help you to guide what I'm doing at what part of the screen, but turns out once I have that, that is basically a laser pointer, not the pen. After that, I cannot write it. Oops. Something is messing it up. Sorry about that. Okay, hopefully now it's working. I'm sharing the screen. So yes, so with that pointer, I cannot write it. So I have to get rid of that. So we talked about motion of mass around our, let's say, head that goes in horizontal circle. When we tie some object like this and then let it go around, right? So I'm not letting it go around because I may worry, I may hit the screen or something like that. But this kind of motion, so why this is going in circle? Because the tension on the string is keeping this mass in a circle. If I let this string go, or if I were to cut this string, the mass gonna just keep its track. Mass will just fly, mass gonna just fly straight. It's not gonna go in circle. So whenever we see something is moving in circle, there must be at least a force that's acting towards the center of force. Okay. And here what we see is moon is going around the earth. So that means there must be a force acting towards the center of the circular path of the moon. Where is that force coming from? And that's where the Newton's comes in. And Newton says, okay, there is this force acting on the moon from the earth, just like the force from the earth acts on us, basically keeps it in that circular path. Okay. So now to describe orbital motion of any satellites or planets, satellites means anything goes that around our planet, we call that satellite. So we have a natural satellite, our moon, we call the moon. Moon is common name for any satellite that's going around any planet. So there are several satellites in different planets, okay? But we have only one moon. But looks like for for I guess couple of months there going to be a new moon that's going around the earth. Okay, it's a asteroid. It's just a passing around. And so since it comes to the gravitational pull of the earth, what happens? So if moon is going around at larger orbit, it is going around the it's going to go around the earth and get out. So for example, if it enters from this side, it's going to go once around and going to get out. Okay, just once. So it's a tiny size of, I think they said a bus or a building. I kind of forgot. Okay. So it's going to get out. So for this, for, for about 2 months, it's going to be our new tiny moon. Okay. It's hard to see. It will be hard to see because too small and too far, but it's going to be there. But other than that, we have only one permanent natural satellite we call our moon, the moon. Okay. But there are several artificial satellites we have put in the orbit that provides communication, for example, for satellite phone, like probably you may have heard new internet provider by company called Tesla, owned by Elon Musk, right? Starlink. So uh, they have like several artificial satellite going around the earth and it provides the internet. So how is that possible? How can we put that thing over there and it just keeps going around? because of this knowledge of the Newton's law of gravitation and Newton's laws of motion. We learned that if we put an object at a certain distance from the Earth and then give a certain velocity, it's going to just keep going around. We don't need firing up engine or anything like that just to keep that moving, because we know Newton's first law of motion, right? And it keeps in circle because of the gravitational pull. So that's the, that's the knowledge. See, it sounds like, oh, force of gravity, laws of motion, what's it gonna do to us? Now, once you can convert that in technology, that makes our life a lot easier. And that's an example of, you know, good use of laws of physics. So in today's class, we will write down the equation of the force of gravity, and then we'll use that equation in Newton's laws of motion to describe the orbital motion of these satellites. Natural or artificial, does not matter. Same physics applies to both artificial and natural. And it's not just, you know, let's say limited to the uh, motion of satellites around the Earth. It can be applied to motion of any object that is going around the larger object. Okay, so that's the beauty of physics. You can apply anywhere. Okay, so now with that said, let me show you the equation for force of the gravity. So according to this equation, it says, okay, it depends on product of two masses. So for example, if we are talking about mass of Earth, and I'm using this notation m with subscript e, uppercase M with subscript e, and mass of the moon, for example, let's say lowercase m. So it's the force between any two mass. So for example, I have fist here, I have another fist here. According to this equation, there is force of gravity between these two fists. In a class, there may be two persons sitting. There are two persons, for example, sitting next to each other. We can calculate the gravitational force between them, okay, using this formula. If there are two masses, and once we have two masses, there we can measure the separation distance. And by the way, when we measure separation distance, it's always from center to center. And that distance is denoted by r, and that's what goes in this equation. But remember, this is not just r, it is r squared, okay? So product of masses, they are on the top of the equation. So that means larger the mass, larger gonna be force of gravity, but r, or the separation distance, is in denominator. That means larger the separation, force going to be smaller. Kind of makes sense, right? When something is closer, they're going to be, like let's say more strong, some sort of connection. And once they are far, that connection becomes less and less. In this case, that connection is the gravitational force. Okay. But, okay, so if it goes farther, it decreases. But it does not simply decrease by that ratio with which it goes farther. For example, if it goes double the distance farther apart, so for example, right now moon is here. Let's say if moon were to go over there, what happens now? The r becomes 2 times the original r we had, okay? So we double the distance. So since the r is being squared, so when we are squaring it, it squares that one as well. So we need to keep that in mind. Oh, we need to square that too as well. Okay. So this whole thing has to be squared. When we square this side, we have to square this whole thing on that side, right? Simple, that little rule of algebra. So that's what this force of gravity equation is saying. Larger the mass, larger the force. Larger the separation distance, smaller the force. Smaller the separation distance, larger the force. So they are kind of inversely related. More accurately, the force is related inverse square of the distance. And force is related directly to the product of masses. So now there is another thing, uppercase G, and it is a constant. Okay, so that constant was determined by doing experiment called Cavendish experiment by putting two masses in some vacuum chamber connected by a rod and measuring the slight twist. They kind of, because of the attraction, what happens is they tend to rotate. And by measuring that torque, which we haven't learned about, but probably you are familiar with the word torque that we use in our everyday life, okay? So by measuring that torque, you can find the force. And once you have force, separation distance, and the masses, you can compute the G. So that's how it was determined by doing experiment, okay? And its value is this here. And you can see this is 10 to the power negative 11 in the exponent. So that makes the force small. How small? So let's do an estimate, okay? So here I have this problem, and this is asking us to calculate force between two persons sitting just 1 meter apart, and their masses are given. Both of them have mass 100 kilogram. So if you are not familiar with kilogram, or if you cannot tell how much mass is there, so my mass is around 65 kilogram. So if you want that converted into pound, for example, you simply multiply kilogram by 2.2, and that's going to give you equivalent pound. So this becomes around 220 pounds equivalent, okay, mass. Actually, pound is unit of force, but we can have equivalent mass as well. So that means they are basically 100 kilogram person. They are relatively heavier person than the average, okay? So now let's figure out how strong the force between them when they are sitting a meter apart. So how long is 1 meter? Oh, this 1 meter thingy doesn't fit in my camera field of view. So if I go all the way back, it is about a meter, okay? So if I were to spread my arm, let's say, so it is up to here. So what is my 1 meter? What is 1 meter length? From my tip of one hand. So if I were to spread my hand from tip to over here is 1 meter long, okay? So that's how far they are separated. So now we have some idea about the mass. We have some idea about the distance between these two persons sitting. So let's calculate the force. So both masses are same. For convenience, I am keeping both masses same. And the separation distance is 1 meter, again, for convenience. So now using this formula, so we are calculating force. At the same time, we are also learning how to use this formula to calculate force. And if force is given, you can just use the algebra to calculate, for example, separation distance and so on, right? So force of gravity is given by that formula. I always copy the formula before I plug in numbers. That way, the person who looks at my work has idea what I'm doing, right? So This is 6.67 times 10 to the power negative 11, and its unit is Newton times meter squared over kilogram squared. And if you are wondering, oh, where is this unit coming from? Basically, it is coming from this formula. Okay, so if I were to solve this one for G, how is it going to look like? So uppercase G going to be F G times R square. And by the way, this lowercase g is subscript. It's not 9.8. That g simply stand for force due to gravity. Okay. Over. And then now I have to divide this by this. So m1, m2. So if I write units, unit of force is Newton, unit of distance is meter. And since distance is being squared, so this is going to have square on it. And unit of mass is kilogram. So kilogram times kilogram means kilogram squared. So that's where this unit is coming from. Okay. So that is just the G. Now let's write the mass number 1, which is 100 kilogram. Now let's copy the mass number 2, which is also 100 kilogram. So that is done. In the numerator, we are done plugging in this number. Now let's put the denominator. There is R squared. Here R is just 1 meter and it is squared. So that means it is, let me write this, it is 1 square times meter square. So you can see this meter square here cancels with this meter square, this kilogram, and this kilogram makes kilogram squared. That cancels with that, leaving the unit just Newton, which should be the case because we are calculating force and unit of force is Newton. Okay. So now we have the unit figured out. 1 square is 1. So that means basically what we have is just these numbers. So there is this small exponent number, and we have this 100, 100, and 6.67. So yes, of course, you can punch that in calculator, but I don't have my calculator handy. What I like to do is I like to use the, work with the exponents. Okay, so if you're not comfortable, let's take a look how it works. So 10 to the power 1 means just 10. Okay, 10 to the power 2 means 10 times 10. Oh, here I should be writing equal sign. That means 100. Okay, similarly, 10 to the power 3 is 1000, and so on. Okay, so here 10 to the power 2, I can write that 100 kilogram as a 10 to the power 2. Now I have 10 to the power 2 here, 10 to the power 2 here, and they are multiplying each other. So when we have same base and we multiply the exponents, what happens? The exponent simply gets added. So 10 to the power 2 times 10 to the power 2 is 10 to the power 4. We just add the exponents. So that's how it works. So if you don't believe me, it's 100, right? 10 to the power 2 is 100, and 10 to the power 2 is 100. So when you multiply that, you get that 10,000, right? 1 with 4 zeros. And when we write 10 to the power 4, that means 1 with 4 zeros. Not 10 with 4 zeros, but 1 with 4 zeros. Now we know these two masses gives us 10 to the power 4. So let me write 6.67 times 10 to the power negative 11. I'm just copying them. And I have 10 to the power 4 coming from the product of two masses. And unit is, of course, Newton. So now, again, they have same base. One has positive exponent 4, another one has negative exponent. So when we add negative 11 and positive 4 together, we get -7, right? 7 plus 4 is 11. So it's going to be 6.67 times 10 to the power -7. And this is Newton. Yeah, this may be a little bit painful for you if you are not used to it. So you can just use calculator. But kind of when you are dealing with this large, very large number or very small number or combination of those, this comes in handy, okay? And you'll be dealing with this kind of number in physics 2 as well if you decide to take physics 2, okay? So that skill may come out handy. I have noticed often when you students punch these numbers in calculator, often they end up making mistake, okay? I haven't looked at everyone's number. Most of them get just right, but some of them make mistake. So just in case if you want to check, this is another way you can do it, right? So now, what is that? Force of gravity between two person is this much. How do I make sense out of that, right? So for that, what I'm going to do is try to simplify this one even more. See, this is 6.67. So it may round to 7 because it's a one sig fig problem. So it's 7 times 10 to the power -7. But for convenience, let's make this force even bigger than that. So I'm going from 7 to 10, okay? So I'm writing this is approximately 10 times 10 to the power -7 Newton. And now you can see why am I doing that? 10 is 10 to the power 1, means this is going to be 10 to the power -6 Newton, which is also means 1 over 10 to the power 6 or 1 over 1 with 6 zeros, and 1 with 6 zeros is million. So how many Newton force is there? 1 millionth Newton, not 1 million Newton, but 1 millionth, because million is in the bottom. So now how much is a Newton? So for example, let's say if you have a small size apple, you put in your hand and you feel it, right? The weight of that apple is about a Newton. So that means what is 1 millionth of a Newton? So what we have to do is cut that small size apple into 1 million pieces. Tough task, isn't it? And just pick one piece and put that in your hand and feel the force. And that's going to be a lot tinier than a fly or mosquito that lands on your hair sometimes, or in your, yes, let's say hair. What happens if a mosquito lands on your hair and if it does not start poking on your head or in your skin, you won't even notice the mosquito is in your body. Why? You don't feel that weight, okay? If I put something like this bigger object, then I can tell, oh, something is my head, okay? But if a mosquito sits in my head, then I wouldn't notice. Why? Because the weight is negligible. So similarly, when there are these two persons a meter apart, they don't notice any force because the force is very small. It's smaller, way smaller than the weight of a mosquito. Okay. So that's why we don't notice, like two persons sitting, you are sitting near the, next to your friend. And if you move away from there, you don't feel that pull, okay? I'm talking about actual pull, not some sort of, lovely attraction or something like that, okay? So that's what the force of gravity, and it is small, and it's small because of this. I mean, when we calculate, the number comes out small because of the small value of this. But when we talk about force between us and the earth, although our mass is only around 100 kilogram when we round up, the mass of Earth is way larger than that. in the order of 10 to the power 24 means 1 with 24 zeros. Don't ask me how to say that number, okay? So that's how big that is. So when we combine that with this 10 to the power negative 11, what happens? This result is that 10 to the power positive 13? See, now it is more than a trillion Newton, okay? And of course, the separation distance also contributes. So what happens is, so because of that, when we are near these large objects like Earth, Moon, we experience that force. But when we are near relatively smaller object like another person or even a building, okay, mass of the building is not enough for us to experience that gravitational pull, okay? So that's the gravitational force, folks, and it always attractive. So that means in case of magnet, what happens? Magnet, they snap, they pull, right? Oh, they pull, but they may also repel. So they may also repel. So there is attraction and repulsion in magnetic force. But in gravitational force, what happens? There is always attractive force, no repulsive force in gravitational force. Okay, so that's why the earth never pushes you up in the sky. I wish it did sometime, but it does not. Okay. Okay, so that's the gravitational force. So now I have a question for you. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So mostly D, but we got all of these choices. So here what's happening? The distance is reduced by half, means R goes to R over 2. Okay. So force and distance, they are inversely related. To be more accurate, it's inverse squared. But see, if R increases, F decreases. That means that's what that is, right? So when we are dividing by larger number, the result gonna be smaller number, like like a pizza. You have a pizza. If you divide that in just by 2 piece, the see the size of the piece you get is, if you divide it into 2 pieces, each piece is going to have that size. But if you divide that into 4 pieces, then each piece is going to have a smaller size. So when we divide by larger number, value becomes smaller. Just by knowing this, we could have eliminated these two. Okay. So now, So in this case, what we are doing is making larger number of pieces means the value is getting, let's see, am I saying the uh, pieces here? So yes, so when you make smaller and smaller number of slices, what happens? So right now, this much, this big. So now if you divide by a smaller number, you reduce by half. So now you are getting larger number, right? So that's why becomes smaller is not the correct choice. We can easily eliminate that. Now between 2 times or 4 times, if this equation had just r, then the r goes to r over 2. So this fraction of fraction, this 2 goes on the top. So it becomes 2 times larger. But since this is not just r, it is r squared, we have to look at this, which is r squared over 4. So that means this, instead of r squared, now we have r squared over 4. And this 4, being fraction of fraction, can be brought on the numerator. So that gives us 4 times more. Okay. So yes, D is correct answer in this case. So if I were to increase mass, mass being in the numerator, the force is going to increase. If I decrease the mass, mass being in numerator, the force is going to decrease. If I decrease both masses, then we need to look at by what fraction and combine both fractions. So for example, if I don't change the r, but I change the mass, let's say this mass goes to m over 2, and this mass goes to m over 2 somehow, and then what's going to happen? We're going to pick 4 in the denominator. Means the force is going to be quarter when we reduce both masses by half. There is no mass squared for each of those. Okay? So that's how this formula works. So that's how this is telling us, how force changes with mass and the distance. Okay? Smaller the mass is, smaller the force. And closer we are, larger the force is, right? So now we've been talking about gravitational pull on us, okay? Gravitational pull of Earth on us. We said, okay, that is weight. We call that weight. And we may denote that by W, or we may write that as a mg, okay? So we said, okay, that weight is force of gravity. And since force is mass times acceleration, and acceleration due to gravity is g, we write F is mg. So that's what we have learned so far. And we said, okay, if we do careful experiment, we get g as 9.8 meter per second square. So that's what we learned so far, okay, in the previous chapter about the weight, force of gravity, and acceleration due to gravity. So now let's use Newton's laws of gravitation and figure out, what this G is, for example. Okay. So since this force is force of gravity on us by Earth, so that means we need to replace this mass, one of the mass by mass of the Earth, and another mass by our mass. Okay, so mass of the Earth, our mass, and separation distance. So when we are near the Earth's surface, or when we are standing at the Earth's surface, remember the separation distance is from center, not from the surface. So you may think, okay, we are on the Earth, so separation distance between Earth and us is 0, which is not. Okay. Since the separation distance is measured from the center of the Earth, so in this case, separation distance between Earth and me or you is equal to radius of the Earth. Okay, so we're going to be using those numbers. So separation distance is equal to radius of the Earth, and its value is this much in meter. Okay, and mass of the Earth just like I said before, it is in the order of 10 to the power 24 kilogram. So it is in the order of thousands kilometer, okay, the separation distance, and it is in the order of, oh, very large number. So now, when we plug in this over here and this mass over here and leave our mass as just m, because if I want to find force of gravity on me, I need to use my mass. If you want to find yours, then you need to use your mass. So I'm leaving that mass as simply m. So when I plug in these numbers over there and also the value of this uppercase G, what do I get? I get this. And that's where this number 9.8 comes from. Okay. And that's what we've been calling G. Okay. So in other words, G is coming from this multiplication and division of these numbers. It depends on mass of the earth and the radius of the earth. Okay. So when we have that, now we can replace this 9.8 by lowercase g and then m. So uppercase G is a fixed constant number, and it is true no matter where you go. But this lowercase g, for example, depends on how far we are from the center of the earth or any other planet. Okay, so lowercase g is distance dependent, but uppercase G is kind of universal. Okay. So now we've been saying, okay, this lowercase g is acceleration due to gravity. Now we know this can also written something like this. F is mg, that means g means F over m, and unit of force is Newton and unit of mass is kilogram. So when I'm writing unit, Newton over kilogram. So in terms of force, we can say, okay, rather than saying acceleration due to gravity, we can say, okay, it is force on mass. What is G? Strength of force on mass. Force per kilogram. Okay, it is force kilogram per kilogram mass. Okay, how much force is acting in each and every kilogram of mass. So it is a strength. And it is also, that term we call, okay, since this force of gravity can act without touching, right? It's not contact, it is a long range force. So even when I'm not touching the earth, it's acting on me, right? So it is a long range force. So how does it act? So to describe, how the gravitational force works, how it can act on another object, the physicists basically introduced this concept, what we call field. Okay. So we call, okay, we have a gravitational field that's surrounding us. That's what we call it. Okay. So what does that mean? So for example, if we have a perfume bottle open in a room, if you enter to the room, you can feel that smell of the perfume right there. You don't have to be very close to the bottle, or you don't have to be touching to the bottle. Okay. So kind of we can say, okay, this bottle of the perfume is creating a field. So that is not actually, the field like a gravitational field, but just to give you some idea. So these days there are these college football, uh, NFL football going on. So a lot of people in the stadium watching the game, right? And if you pay attention, what do you see? ball gets thrown and all the heads of these, the viewer or the audiences that goes, gets pulled by the ball, although the ball is not touching us. So maybe we can say, okay, this ball is creating some sort of field, and all these people are attracted to that ball, so they keep watching it. Okay, so similar idea here. What happens? We say, okay, any mass produces a field around it, and when another mass is there, it experiences force. And how much force it experiences? 9.8 Newton per kilogram for the from the earth when it is near. Okay, but that changes as the distance changes. So this G is called gravitational field strength. So this proper name is gravitational field strength. And when we talk G in terms of gravitational field strength, then we use the unit Newton over kilogram. Okay, but it is no different than basically meter over per second square. It's same as that. It's just written slightly differently. And we can see that easily if we expand the Newton. Remember, Newton is mass times acceleration. Force is mass times acceleration. So unit of force is kilogram and acceleration is meter over second square. So that is Newton, and kilogram down there, kilogram. So this kilogram cancels, giving you just meter over second square. So basically they are equivalent, but depending on what concept we are trying to describe using that little g, we may write Newton per kilogram or meter over second squared. Okay, so that's about the unit of G. And what is the meaning of G? The G is not always 9.8. It is 9.8, lowercase g is 9.8 only when it is near the Earth's surface. If we go above the Earth's surface, what's going to happen? See, now the separation distance is not equal to radius of the Earth. Once we go above the Earth, what happens? This is not just radius of the Earth, rather it's going to be radius of the Earth plus whatever height we go from the surface of the Earth. So that's what we want to write now. So just like the R can change, similarly mass can change. For example, if you are on the moon or on the surface of the Mars, the mass not going to be mass of the Earth. It's going to be mass of the Mars or the moon, wherever, planet or the satellite you are in. So that's why this going to be just general mass, okay? And if you are standing on the sun, surface of the sun, and if you want to find value of G, then you need to use mass of the sun and radius of the sun in that case. Okay, so the G can go from 0 to very large value. Okay, so keep that in mind, lowercase g. Uppercase G, that's a different story. It is a fixed value. It has a universal value. The number you saw, 6.67 times 10 to the power negative 7, that's a fixed number for that unit, given unit, okay? So now let's look at this equation more carefully. Larger the mass, larger the value of G, and larger the value of R, smaller the value of G for the same mass, and smaller the value of R, what happens? Larger the value of G. for the same mass. So it depends on mass and the separation distance between, I mean, it just depends on how far the point of interest is from the large mass. Okay, so that's what that is. So just like I was saying, when we are here on the earth, value of G is about 9.8. Now, G on the moon is about 1/6 G on the earth. Only about 1/6. Why? Because mass of the moon is way smaller than the mass of the earth. Although radius of the moon is also smaller, but what happens is the mass is way smaller for the moon compared to the earth. So, so that's for the, let's say, moon, value of G becomes smaller. Now, let's say if I were to go to the sun, what happens? Mass of the sun is way larger than mass of the earth. So because of that, value of G on the sun becomes larger. Okay, how much? I haven't that in my head. Okay, I have to find numbers, but what I know is it's a lot larger than on the earth. And there are stars that are way larger than our star, the sun, right? So there are several billions of stars that are way larger than the sun. So what that means, the value of G on that star gonna be even larger than the value on the surface of the sun, assuming that, you know, their mass becomes really large. So now what happens is these stars are born, they die, they you know, they have this life cycle. If we talk about life cycle of our sun, it is kind of in the middle age. So we believe or estimate, we estimate the age of our sun is around 10 billion years. Total age, lifespan, I should say. Right now, it is around 5 billion years old. Okay, so our sun is hot, it provides heat and light because there is nuclear reaction going inside the sun. So basically, these large stars, they have a lot of hydrogen gas, and those hydrogen gas fuse together to produce helium and higher elements. In that process, they emit a lot of energy. So you can think of that those hydrogen are burning inside the star. But eventually what happens? They basically, the fuel runs out. And in that case, when it's burning in the outside, they kind of explode. We call that supernova explosion for the stars. And after explosion, what happens? Most of the mass comes back because of the gravitational pull. Now the size becomes really small. So mass is about the same, but the size of the star is really small. Mass is about the same, but the radius is really small. So really small radius, but the same mass makes the value of G really large. Okay, really large. And what happens in that case? So for example, here, right here on the Earth, if Earth was the star and if you were to, you know, like let's say explode and then behave like a star, those big star, then after explosion, the size of the Earth would be about the size of the basketball. Imagine, right now, the size of the Earth, and then after explosion, size of the basketball. It becomes to the size of the basketball. By what factor the value of R decreases? You can just only imagine, right? So similar size shrinkage happens in this case of these big stars. So the stars that are bigger than the stars that has mass larger than 10 times the mass of the sun, when they explode, what happens is they turns into what we call black hole, where the value of G is so large that even when you shine a light from the surface of those black hole, what's going to happen? Let's say you shine a laser light. The laser light behaves as if like a ball we throw here. So what happens when we throw a ball here? It goes up, comes back down to the earth. Over there, what happens? That laser light goes and bends back and comes back. So that means the light cannot escape. Even the light cannot escape from that body. Okay. Over here, light can easily escape. If we shine laser light, it does not comes back, bouncing back. Okay. It just escapes. So that's why the name black hole. If no light escapes from the object, that means it's not reflecting any light. It's even if it is producing light, that light is not coming. So that means we cannot see. So it is a dark. Okay. Just like in the night, if all the light is turned off, we cannot see what's inside the room. Okay. Why? Because when we turn on the light from the light bulb hits our body reflects the light, and that light comes to our eyes, and that's how we see the object. In black hole, the black holes, they don't reflect the light, they absorb the light. Okay. So because of that, we cannot see it. So there are maybe millions or billions of black holes in our universe, including one big black hole at the center of our galaxy. Okay. So this simple idea, see, this simple idea kind of helps us to understand why the black hole behaves the way it does. Okay. So that's the beauty of physics. So it can describe the nature, okay, what's going on in the nature and so on. Okay. So that's that. And I see there is a question there. Do you think the sun will ever explode? Of course. I don't think. I can tell it's going to explode. In when? Not today, not tomorrow, not in our lifetime. That's the good news. Okay. It's going to explode in about 5 billion years. Okay. So it looks like it's a good time to take a break. It's already 11:05. So I'll pull on this one after we come back from the break. So it says 11:05. So we'll be back in 11:10. Okay, folks? Okay, folks. So welcome back. Here is another clicker question. Let's see, what do you think? 30 more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, so mostly C. So yes, increase in the distance. That is correct answer. So gravitational field strength G Gm over r square. Okay. If we are talking about Earth, this is going to be mass of the Earth. So when does G becomes smaller? When R becomes larger. So that's what that equation is saying. So now I think I have another question for you between uppercase G and lowercase g. Keep in mind that we talked about that, and they appear in the equation something like this, right? So you have a minute for this. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. So let's see what we got here. Mostly B, and that is correct answer. G is universal, but G is specific. It depends on mass of the bigger, or let's say mass of the planet, or could be even moons, any large mass. Okay, with that, now let's move to the circular orbit of satellites and planets. So our natural satellite is Moon. So this is our moon, so that's why it is the moon, not a moon. And this is Earth, right? So now we learn about the gravitational force inside out. So now we are learning about how the gravitational force keeps object in circular motion because it acts towards the center of the circle. And now we learn how to use Newton's law in that case, or Newton's laws of motion, or simply laws of motion, right? So force of gravity between any mass and the mass of the Earth is given by this equation. And see here, I did not write this as a radius of the Earth. It's not, because Moon is not here at the surface, on the surface of the Earth, okay? It is above. So this r is distance measured from the center as shown in this diagram here, okay? But if we measure from the surface, for example, here I'm showing on this side, but you can think of that is same as this one as well, right? So that was for just the clarity. This is the radius of the Earth, which is same as this one, right? Now, if you are standing here and measuring the, distance of the moon, then we may say, okay, that is the height of the moon from the Earth, because we are measuring not from the center, but we are standing on the surface and we are measuring from there. So for example, what's my height? When I measure my height, I don't measure from the center of the Earth. I just measure from the surface of the earth and how far I am. What's the height of the building? We do the same thing. We measure from the surface, not from the center. So when we are measuring some height, distance from the surface, then we have to add this radius so that we get to the center, because we need the distance from the center in this formula. Okay, so we can do that. So now with that said, let's use Newton's law in this situation. So force of gravity in that direction means the radial acceleration is in the same direction, and the circle is like that. So I can use or write Newton's second law for circular motion. Sum of forces in radial direction is equal to mass times acceleration. Okay. So all force is force of gravity. There are no friction force, no normal force, nothing there. Okay. And so that is the equal to the weight of the moon at that point. Weight of the moon, or that weight comes from the gravitational pull from the earth. And so that means there is only one force that's acting in radial direction. And if we choose towards the center as a positive, then acceleration is also pointing towards the center of the circular path. Now we can write this equation. This is gravitational pull on the earth, on the moon, where m is mass of the moon, lowercase m, and so is this one, because this mass is mass of moving object. What is moving here when it is going around the earth? It's the moon that's moving. So this mass is also mass of the moon. Okay. So now what do we see here? Very interesting. The mass cancels. So that means we don't have to worry about mass of the satellite. For example, when we are putting the satellite in an orbit, if we are trying to figure out what should be the speed or how far it is, okay, we don't have to worry about the mass. Yes, we have to worry about mass while lifting it and bringing at that point and putting that in motion. But once it goes to that motion, what happens? Once the velocity is fixed, then it does not depend on mass. That's what it is saying. Okay. And there is no other mass, which is mass of the Earth, in this case for the Earth satellites. So I see there is r squared and there is r. So that means I can cancel one of the r. So that gives me, I can solve this one for v. Okay. So I'm left with z mass of the Earth over r is v squared, right? So now v is just the square root of that thingy, and that's what I'm writing here. Okay. So speed simply depends on speed of satellite around the Earth, simply depends on how high it is, or how high we want to put the satellite. So for that, we can calculate the speed, and we bring the satellite up there in the space and give that speed tangential velocity, that value, and then it will just keep going around. And there are several artificial satellites going around the Earth and littering the Earth at that, I mean, littering the space, I should say. Okay. So this is the speed of the satellite around the Earth, which does not depend on mass of the satellite, but it depends on mass of the Earth. And similarly, we can use the equivalent equation to find speed of Earth around the sun. So when we're talking about Earth going around the sun, what happens? Now the Earth is the satellite of the sun. We call planets, okay? So these planets are like satellites for the sun. So mass of the planets cancels. So the speed simply depends on mass of the sun in that case, mass of the sun in that case. And since we know how far the Earth is from the sun, we can calculate the speed of this Earth. We can actually also measure the speed, but we can calculate. That's easier way to do it after knowing the distance. And it turns out that it moves around 30 kilometer, not per hour. No, it is 30 kilometer per second. Imagine how fast it is moving. How fast Earth is moving around the sun. Speed of Earth around the sun. 30 kilometer in 1 second. I live around 18, 20 miles, 20 miles drive from campus. Okay. Where I live, it is around 20 miles drive. So if I convert that 20 miles into kilometer, it is around 32 kilometers. So now let's say somehow if I could move with the speed of Earth, then I'll be home in 1 second from campus. But with traffic and all, it takes half hour to 1 hour. Okay, it depends. See how fast the Earth is moving. Imagine that. Moving 20 miles, nearly 20 miles in a second. How much is 1 second? About a snap. One Mississippi, right? Probably you guys learned that. So that's how fast Earth is moving around the sun. So you can use the same formula there. So you find any object going around another large object, you can find the speed if you can measure how far that object is from that bigger mass. Okay. And that's how, when we discover exoplanets. What is exoplanets? Our planets are the planets around our sun, but there are planets. We have discovered several planets around other stars. So when we discover that, we use the same physics to find out how fast it is moving or how far it is, and so on. Okay. So this law of gravitation, laws of physics, they are universal. They apply everywhere. Okay. So here is an example I have done in my note. So I just brought the screenshot of that. Okay. And this is real number. The moon is that many kilometers from the center of the earth. How fast it is moving in the orbit. And for that, we need mass of the earth. And that's what I'm writing here. Okay. And radius is given in kilometer, but for that formula, we need that in meters. And mass of the earth has to be in kilogram, which is already in kilogram. That's good. So it says find V and A. The speed, we can just use this formula since mass is given, R is given, and we already know the value of this uppercase G. We can just plug in and calculate. So that's going to be in meter per second. And in kilometer per second, it is about 1 kilometer per second. Still, how fast is the moon moving around the sun, Earth? 1 kilometer per second, around 1 kilometer per second. If you have no idea how much 1 kilometer is, then this is about 0.6 miles, slightly more than half miles. Okay. In 1 second, it moves half miles, more than half miles in 1 second, moving really fast as well. Of course, Earth is moving way faster than the moon around the sun. Okay. But this is the speed of the moon around the sun. That's what we calculated. And now it is also asking you to find the acceleration in the note. I don't know if I calculated it or not. I don't quite remember at this moment, but once you have that, you can use this v square over r, radial acceleration. Basically, that's what it's talking about. So speed you just calculated, use the meter per second, and then r, we have already r over there. So once we do that, we get the acceleration of the moon as well. Once you have speed and radius for object that's going in circle or part of circle, you can find the speed using that formula. And direction of the velocity is always tangential to the circle at the moment, right? So if Earth is there and Moon is there, if it is moving something like that, that's the direction of velocity, tangent to that part of this circle at that point. If it is here, then that's the direction of velocity. So that's how it works in the circular motion. We know that, right? So now, with that, I have another question for you. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So we got all of them. Period of rotation, materials used to build satellite characteristic is independent of the mass. So for example, if you made a satellite out of iron versus wood, probably the mass gonna be, it's gonna be kind of different, I guess. So it's not gonna be independent of mass. The gravitational force acting on the satellite. So gravitational force between any two objects is given by m1, m2 over r square. So it depends on both masses. Now, period of rotation, how fast it rotates. Oh, looks like we haven't talked about period, but we'll see soon. So period, yes, does not depend on mass. It does not depend on speed, and it does not depend on, I mean, the speed does not depend on period. Sorry, speed does not depend on mass, And period also does not depend on mass because speed for object that's moving in circle or part of circle with radius r, say the distance over time. So that means distance is circumference of that circle. So circumference of a circle of radius r is 2 pi r, and time it takes to go once around is we call period. Okay, so that's what the period is. So since we learned that speed does not depend on speed does not depend on mass, for example, so that was the equation. So it is not the mass of the satellite. This is mass of the Earth. Okay. So it does not depend on mass of the satellite. So speed does not depend. And the period of rotation, see how it is related. So we can see by just looking at this equation and plugging in there. See how T also does not depend on mass of the satellite. So yes, this is correct. Now, how about the acceleration due to gravity acting on the satellite? Acceleration due to gravity of the satellite. So acceleration due to gravity, what did we learn about that? It was Gm over r square under the square root. Oh, I think it wasn't the square root. Yeah, it is mg gmm over r square. So no, there is no square root. Looks like this gonna be also, there is no mass of the satellite as well. Okay, so there is no mass of the satellite here, mass of another object. So it looks like this is also incorrect. So the only correct choice in this case seems to be A. Probably I should have asked this question after I talked about period. That would have been better, I guess. So A is the correct answer in this case. So that's why a lot of confusion here. So here is another question that you should be able to tell. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what happens here. So mostly B, and that is correct answer. How do I know? Speed is the mass of the Earth over radius under the square root, so it does not depend on mass of the satellite. So that means weight depends on mass, so larger mass, larger weight, same mass, same weight. So since it does not depend on mass of the satellite, their speed V1, V2 gonna be equal no matter whether they are larger or smaller, okay? So that's why B is correct answer. When we are here, let's say we have two satellites, but at separate distance. For example, this is R1 and this is R2 bigger. So R2 is bigger than R1. And you have satellite V1 and you have satellite V2. Sorry, the speed of satellite, this outer satellite is V2 and inner satellite is V1. Which speed is larger? So I'm making clicker question here. A, V1 larger, B, V2 larger, C, V1 and V2 are equal, D, need mass of satellite. To figure this out. Okay, so I'm opening this poll and you have 30 seconds, okay? What do you think? Five more seconds. 5, 4, 3, 2, 1, and it stops. So let's see what we got here. We got A and C kind of competing, A a little bit more. So looking at this equation, so to find the speed, we like this and see it depends on distance. Speed and R, they are inversely related. So what that means, larger R means smaller speed, or smaller R. So in this case, this R1 is smaller than R2, right? It is closer. R1 is smaller means B is larger. So B1 is larger. See, the speed is equal only when they are at the same distance, okay? But if one is farther, then it's going to be moving slower. For example, we saw a moon at that distance. Speed of that moon was around 1 kilometer per second. Let's suppose we have a something like, really strong thingy, Hulk like a thing, okay, that can throw an object from top of mountain, okay, very close to the Earth's surface. If it is going around the Earth at that distance, very close to the surface of the Earth, the speed of that object is going to be 8 kilometers per second. See, moon being farther, it has a speed around only 1 kilometer per second. But if something was going very close to the surface of the Earth, the speed would be 8 kilometers per second. Okay, so closer the object is near, to the Earth, it must be moving faster to keep in the orbit. Otherwise, it's going to just crash on the Earth if it goes slower. So for example, if somehow moon, like let's say get pushed inside. Let's say the asteroid we just talked about, let's say, if it happens, it's not colliding with the moon, but let's say if it were to collide to the moon and push the moon inside, then there were two possibilities. One just crashes on the earth, another one comes close to the earth and then it starts moving faster. Okay. In that case, moon would look a lot bigger once it comes closer to the earth. So anyway, so that's how this thing works. So it is mass independent. The speed of the satellite is mass independent. That's the main thing we learn. And how the speed changes with the distance. Okay, that's the another thing we learned. Now, period of satellites, just like I was saying, we can use the same equation of the speed and write speed as a distance over period time. So this time is the period. And then now we can solve for period. But here what we have is square root. If we want to solve for t, we need to do two things. One, get rid of this square root. Yeah, we don't have to, but there is r over here, r here. So if we want to combine both r at same place, then we need to get rid of this so that we can combine the r. So for that, what I'm doing is I'm squaring this and squaring that. So squaring this simply get rid of. So on the left-hand side, it becomes 4 pi square r square over t square. On the right-hand side, it's simply Zm over r. So this r square can come here. So it becomes 4, and then 4 pi square, it can also come down there. So it becomes 1 over t square is Gm over 4 pi squared, r square here, so it becomes r cubed, okay? But we want t squared or t, so that means we need to flip this. So when I flip this, this 1 over t square becomes t square, and this gm over 4 pi r cube. So you see this 4 pi square r cube goes on the numerator. See, although it's written outside, it is still a numerator. We can write this as a denominator over there. Gm, which was in the numerator, becomes denominator. Once we flip it or we switch the sides, whatever way you like to see it. So now what do you see here? Square of the period is proportional to the distance of the satellite from the Earth. Or if we are talking about planets, that's going to be distance of the planet from the sun. So same equation applied. So this equation was first given by Kepler, not in this form, slightly different form, before Newton, just by observing. So what Kepler did was he just followed the path of this planet. So first he, recognized, okay, the Mars is there on the sky. I can see Mars. I can see Venus. So he just spotted the position and made the plot of those position. And then turned out that they move in circle, not perfect circle, but slightly oval called ellipses. And that was the first Kepler's law. And there is second Kepler's law that tells us, why it's moving faster when it is closer to the planet in the elliptical, and which we already talked about from this equation. And all these were just discovered by Kepler before Newton discovered the law of gravitation. Okay, but now we have a bit more complete information about that by using the Newton's law. So Kepler's discovered this by just purely doing experiment and making plot and then doing some, very simple calculation without using laws of motion. Okay. So that is kind of strength of experiment in science. Okay. You can discover things just by doing experiments. but it's better if you can verify that doing the math later. And that's what we can do after learning the Newton's second law of motion. Okay. Now, why this equation is important? For example, this is called third law, Kepler's third law. Yeah, one of the Kepler's law. So here what we have is now, for example, let's say this communication satellites, I talked at the very beginning that, you can have satellite phones, internet from the satellite. So what happens is they put satellite on top of a particular city, and that satellite provides that signal. So we don't want that satellite shifting or drifting away from that sky on there, right? So for example, if I put a satellite to provide some information here in Denver, I don't want that satellite to be shifting to the Canada or maybe some another state or something like that. So I want that always on top of the Denver. Let's say this is Earth, Denver is this, and here I want satellite. And I want that satellite all the time. So satellite has to orbit the Earth. And at the same time, Earth is also spinning. We know Earth spins once in 24 hours. So if we make period of the satellite 24 hours, then what's going to happen? It's going to stay always on top of that city, that place on the Earth. So now, if we use period 24 hours, we can calculate how high the satellite has to be. So we put that satellite precisely at that point so that it always stationary with respect to the Earth's surface there. So that's why the name geostationary satellites. Okay. So that's how these communication satellites are placed. So all of them have to be on the same height if you want them to be in the same place. So that's why that particular height in the sky from the Earth is cluttered with all these artificial satellites. All of them are, one is just behind another one, all of them moving with the same speed. So because of that, chance of collision is kind of almost zero. So that's how this thing works. So this is the circular motion of objects above the Earth's surface, okay? So next class, we'll start talking about the third main idea in physics, conservation laws. But before we start conservation laws, we need to learn some vocabularies, and that's what we're going to be doing next class, work, energy, and so on. And after that, we can talk about conservation of energy. So I'll see you folks in next class.